Welcome to this video. And in this video, we discuss the concept of solutions of linear time invariant discrete time state equations. The solutions of linear time invariant discrete time state equation. In my previous video, I discussed the process of determining or writing the state space model of discrete time systems in the various canonical forms. That is the controllable, observable, and the diagonal canonical form. And in this video, I discussed the concept of determining the solution of the linear time invariant discrete time state equations. We consider the state equation of a discrete time system defined by the state equation x of k plus 1 is a matrix G x of k plus h u of k, and the output is given by y of k is the matrix C multiplied by x of k plus d u of k. The solution of the state equation for any positive integer k may be obtained directly as follows. So we take x of 1 to be equal to g x of 0 plus h u of 0 as our equation 1. We can take x of 2 to be equal to g x of 1 plus h u of 1, which is the same as g into x of 1 can be written as gx of 0. This is gx of 0 plus h u of 0 and then plus h u of 1, which you can write as g squared x of 0 plus g h u of 0 plus h u of 1, which you can call equation 2. Similarly, we can write x of 3 to be equal to x of 3 can be obtained as g x of 2 plus h u of 2, which upon expansion, we expand and replace x of 2 into equation 2, then we can write these as g cubed x of 0 plus g squared h u of 0 plus g h u of 1 plus h u of 2. This is equation 3. If we look at equations 1, 2, and 3, we can obtain the general expression for x of k as follows. Our x of k can be generalized to be equal to g power k x of 0 plus the summation of the terms from j is equals to 0 to k minus 1 of g power k minus j minus 1 multiplied by h u of j, where k is the terms 1, 2, 3, all the way to infinity. So this is the general expression for the solution of k when we compare equations 1, 2, and 3. Also, given the state equation, x of k plus 1, x of k plus 1 is equals to g x of k plus h u of k. We can obtain the z transform of the state equation as z x of z minus z x of 0 will be equal to g x of z plus h u of z. If you collect the like terms together, then we can write this as zi minus g into x of z will be equal to z x of 0 plus h u of z. From which, if we divide both sides by zi minus g, we can obtain x of z to be equal to zi minus g inverse multiplied by z x of 0 plus zi minus g inverse multiplied by h u of z. If we take the inverse Laplace transform of this equation, our x of k can be written as the inverse z transform of zi minus g inverse z x of 0 plus the inverse z transform of zi minus g inverse h u of z. We can call this equation A and this equation B. Equations A and B are both the solutions of our state equation. In other words, they are the solutions of x of k, consisting of two parts. And from these, we can note then as follows. The function g of k, g power k, will be compared to the first term, which is the inverse z transform of zi minus g inverse. And then the summation of the terms that we have will be the inverse z transform of the second portion. Therefore, we can write as follows. Our g power k is equals to the z inverse transform of zi minus g inverse multiplied by z, and our summation of the terms from j equals 0 to k minus 1 of g power k minus j minus 1 multiplied by h u of j is equated to the z inverse transform of the second part, which is zi minus g inverse multiplied by h u of z. We can have this as equation C and this as equation D. Equation C yields g power k, which is z inverse zi minus g inverse multiplied by z. And this is called the state transition matrix, which is similar to the state transition matrix as covered under the state space representation of time continuous system. And it is the matrix that contains all the information about the free motion of the system, such that with the information of the free motion of the system, then together with the information of the response of the system to the input, we can obtain the solution of the state equation. And the solution of the state equation will be obtained as from equation B, given by x of k consisting of two parts, the Z inverse transform of Zi minus G inverse multiplied by Z x of 0 plus the inverse Z transform of Zi minus G inverse multiplied by H u of Z. Let's put this into perspective by form of an example. The question is, obtain the state transition matrix of the discrete time system defined by x of k plus 1 is equals to g x of k plus h u of k, and y of k is cx of k, where the matrices G are, G is the matrix 0, 1, minus 0.16, negative 1. Matrix H is the matrix 1, 1. The matrix C is the matrix 0, 1. So that is the question. We have to determine the state transition matrix for the system defined by the state equation and the output equation, where the matrices G, H, and C are given by the matrices respectively. We are also to obtain the state x of k and the output y of k. We are to obtain x of k and y of k when the input u of k is equals to 1 for all values of k. And we assume the initial state of the system as x of 0 to be equal to 1, negative 1. So the initial state x of 0 is 1, negative 1. So we first determine the state transition matrix. Then we determine the state x of k and the output y of k with the assumption of the initial condition of the systems as x of 0 is equals to 1, negative 1. Let's look at the solution to our problem. For the state transition matrix G power k, this is obtained as the inverse Z transform of Zi minus G inverse multiplied by Z. So we first determine Zi minus G, and our Zi minus G, will be obtained as follows. So Zi minus G will give us Z negative 1, 0.16, and Z plus 1. Our Zi minus G inverse will be equal to 1 over the determinant, which is Z squared plus Z plus 0.16 into, then we interchange the terms of the major diagonal to get Z plus 1, Z, and we negate the terms of the minor diagonal to obtain 1, negative 0.16. Then next we determine Zi minus G inverse multiplied by Z, which can be written as Z over Z squared plus Z plus 0.16 into Z plus 1, 1 minus 0.16 Z. So we would wish to obtain the partial fraction form of our matrix so that we can obtain the inverse Z transform. That means we need to write the denominator in terms of its factors. Z squared plus Z plus 0.16 can be written as Z plus 0.5, sorry, 0.2 into z plus 0.8. The terms are 0.2 and 0.8. That means we need to get the partial parts of z plus 1 over z plus 0.2 into z plus 0.8. Then we get the term 1 over z plus 0.2 into z plus 0.8. We also get negative 0.616 over z plus 0.2 into z plus 0.8, and the term z over z plus 0.2 into z plus 0.8. So those are the partial parts we need to establish. And determining the partial parts, then we'll multiply all of them by z. And if you work out the partial parts, we'll obtain zi minus d inverse multiplied by z to be the partial parts as 4 over 3z over z plus 0.2 plus negative a third z over z plus 0.8 as the first part, and have 5 over 3z over z plus 0.2 plus negative 5 over 3z over z plus 0.8. Then we get the other part to be negative 4 over 15z over z plus 0.2 plus 4 over 15z over z plus 0.8. Lastly, we'll get negative a third z over z plus 0.2 plus 4 over 3z over z plus 0.8. And those are our partial parts. Then we can get our g of k, which is the inverse z transform of zi minus d inverse multiplied by z. That means we get the inverse z transform of each of the parts that we have. The first one will give us 4 over 3 multiplied by negative 0.2 power k plus, that's negative a third, so minus a third, negative 1 over 3 into minus 0.8 power k. Then the second part will be 5 over 3 into minus 0.2 power k minus 5 over 3 into minus 0.8 power k. Then you'll have minus 4 over 15 into negative 0.2 power k minus plus 4 over 15 into 0.8 negative power k. Then negative a third into minus 0.2 power k plus 4 over 3 into minus 0.8 power k. And that is our state transition matrix as obtained by determining the inverse z transform of the previous function. Next, we need to solve for the state and output equation. We need to solve for the state and output equation. And from our expression of x of z using this expression, okay, we can write x of z as follows. So our x of z can be obtained as zi minus d inverse into zx of 0 plus hu of z. Okay, that's our x of z. We take z multiplied by x of 0 is the same as z multiplied by x of 0. The initial conditions of the system are given as 1 and negative 1. And therefore, this one will give us Z and negative Z. Next, we need to get H multiplied by U of Z. Our matrix H is given as 1, 1. U of Z, we are given that U of K is equals to 1. That means U of Z is the same as Z over Z minus 1. And therefore, we multiply this by Z over Z minus 1 to obtain Z over Z minus 1 and then Z over Z minus 1 as a matrix. Next, we sum the two. Z x of 0 plus H U of Z will be Z negative Z. And then we sum with Z over Z minus 1 and Z over Z minus 1. And when you sum these, we will obtain the following. So the first term will be Z squared over Z minus 1. And the second term will be minus Z squared plus 2Z over Z minus 1. Next, we need to multiply the entire term Z into X of 0 plus HU of Z multiplied by the Z inverse, Zi minus G inverse as follows. So Zi minus G inverse, we already obtained these as 1 over Z squared plus 0. Plus Z plus 0.16 into then our function as Z plus 1, 1, negative 0.6, Z. Verify you back to our Zi minus G inverse. This is our Zi minus G inverse, which we proceed now to multiply Zi minus G inverse into Z x of 0 plus H U of Z will therefore yield 1 over, so this term will be Z plus 0.2 in its factors, Z plus 0.8 multiplied by Z plus 1, 1 minus 0.16 Z. This is 0.16 multiplied by the terms Zx of 0 plus Hu of Z, which we have obtained as these terms. So allow me write this as Z squared over Z minus 1 negative Z squared plus 2Z over Z minus 1. When we multiply them out, we notice we'll have now 3 terms because of the Z minus 1 as 1 over Z minus 1 into Z plus 0.2 into Z plus 0.8 into, and then we multiply the terms that we have as Z plus 1, 1 minus 0.16 Z, and we multiply this by Z squared and minus Z squared plus 2Z. If you work out those matrices, then we'll obtain the following, which will be equal to 1 over, so the 3 terms are Z plus 0.2, Z plus 0.8, and Z minus 1 into the first term will give us Z squared plus Z or plus 2. We get this as Z squared plus 2, and then we'll have minus Z squared plus 1.84 multiplied by Z. So we need first to write these into partial parts, and then we multiply by z. The partial parts are 3 terms: a constant over z plus 0.2, constant over z plus 0.8, and a constant over z plus minus 1. Then once we have the partial parts, we multiply them by z. If you obtain the partial parts, ideally we are supposed to have a constant a over z plus 0.2 plus a constant b over z plus 0.8 plus a constant c over z minus 1, then a constant d over z plus 0.2 plus a constant e over z plus 0.8 plus a constant f over z minus 1. All these we multiply by z. If we evaluate those terms, we'll get negative 17 over 6z over z plus 0.2 plus 22 over 9z over z plus 0.8 plus 25 over 18z over z minus 1. Then on the denominator, on the second row, we'll have 17 over 30 z over z plus 0.2 minus 88 over 45 z over z plus 0.8 plus 7 over 18 z over z minus 1. And this is our x of z. To get x of k, then we need to get the inverse z transform of each of the parts that we have. Considering that z over z plus a maps to a, negative a power k, we have this. Then each of the terms, our a term is the constant in the z plus 0.2, z plus 0.8, and z minus 0.1. That means then we can write our terms as follows. Our x of k will be obtained as negative 17 over 6 into minus 0.2 power k plus 22 over 9 into minus 0.8 power k plus 25 over 18. Then we'll have 17 over 30 into 0.2 negative power k minus 88 over 45 into minus 0.8 power k plus 7 over 18. And that's our x of k. Finally, our output y of k, which is c multiplied by x of k. Our matrix C was given as 0, 1. So you'll have 0, 1 multiplied by x of k. That means the first row will collapse and we'll be left with the second row as our y of k, which is 17 over 30 into minus 0.2 power k minus 88 over 45 into minus 0.8 power k plus 7 over 18. And those are the solutions for the state and the output of our given problem. Otherwise, that is the end of my presentation, and thank you for watching this video.